Okay, so last time we were talking about curl, and let me just remind you, just a little bit of context. We're doing a kind of a, in advance preview of what we're going to discuss in much more detail with much more sort of, developed tools that we'll be able to take advantage of and perspectives that we'll understand, and all of this will get much more of a justification for what I'm basically asserting here. But nevertheless, these are good geometric ideas to start sort of chewing on a little bit. And so reminder, we have this thing called curl, computed, which we denote like this to motivate this symbolic formula for how to compute it. Again, very convenient notation. Again, this is the most common notation that you're probably going to see for curl. And again, it represents, in some sense or another, hard to make this precise, but to what extent is there there's kind of a rotation happening within the fluid. And so the standard first example, and this is where we left off last time, is this vector field right here, which, again, make sure you can do this. Make sure you can think through, what this tells you about this vector field. Persuade yourself that it looks kind of like this. And by the way, I only drew kind of a horizontal slice of this vector field. Right? This vector field exists all throughout R3. So I drew just what it looks like in the XY plane for kind of artistic reasons. Right? I mean, it's going to be a muddled picture otherwise. So you can see physical intuition, geometric intuition, that the fluid is kind of rotating. Right? And as predicted, as it should, curl, which ends up being 002 in this case, which is that vector, notice that defines an axis, and indeed this is the axis that the fluid is rotating around. Again, this doesn't prove anything. All this is an example of what I'd claimed. Right? So this is a plausibility check, you might call it. But anyway, hopefully at least somewhat satisfying. Here's another example. Now this is a quickie. Again, make sure you can take this formula and persuade yourself of this picture of this vector field. Good exercise to think through. And of course you can compute the curl. Turns out to be the zero vector, suggesting that there's no circulation. And now let's, does that make sense? We look back at this picture here, and I don't see any rotation happening in the fluid here. Right? So again, I'm going to put that in the win column. This is what I would call intuitively satisfying. And good. All right, last example is a little tricky. It's going to appear, at first glance, to be a failure. This is going to appear to be a counterexample. And I'm going to try to explain to you how it's not. This is just an example of how what we mean by the rotation of the fluid is a subtlety. And it's not as obvious as a lot of students think it is. So again, here we go. Formula. Vector field. Again, make sure you can do that. I'm going to say at a glance it looks like there isn't any rotation, because look at these sort of obvious flow lines. All of these flow lines are straight lines. Not hard to persuade yourself from the picture. I mean, you can see it right in the formula. The vector field, all of the field vectors point only in the x direction. So the flow lines are always parallel to the x-axis. And yet, weirdly, seemingly inconsistent with our interpretation, you compute curl, and you get a non-zero vector. That would suggest that there is some rotation happening in this fluid. And a lot of students, very reasonably, don't want to accept that there is a rotation happening in this fluid. Where's the rotation? Every single particle of water is going in a straight line. Okay, so here's the subtle distinction. When we talk about the rotation of the fluid, we're not talking about rotation of individual single particles of fluid. It's just not what circulation is. Now, how were you supposed to know that back here in this definition? You weren't, right? I pointed out this is kind of a hard thing to describe. right? And then what do I do, but if not my very first example of rotation of a fluid, and I show you an example where individual particles, like, again, if you were to take this vector field, draw the flow lines, not hard to persuade yourself, you would get circular flow lines, right? And that kind of gets you thinking from a mindset point of view that, hey, the flow lines tell the story. They don't. So let me try to show you where I'll get to you in just a second. Where are the flow lines here? Or excuse me, where is the rotation here? And think of it in these terms. Imagine that this is the flow of water on the surface of a river or a creek or something like that. It'd be a weird little situation, but let's say. And now imagine that there's a little leaf that has fallen down. It's that time of year, right? And the leaf falls into the surface of the river, and what happens? And, well, among other things, notice that on this side, what you might call, from this point of view, the left side of the leaf, the water is flowing into the page. On the right side of the leaf, the water is flowing out of the page. Now, there's a temptation to say, well, then that's why it's not moving, because it's being pushed in two different directions. But it's being pushed in two different directions on two different sides. Let me say it a little bit differently. This leaf, from what's happening on the left side, it's being pushed clockwise. From what's happening on the right side, also clockwise. Right? So just imagine that you're again looking at this leaf down in the little creek or river. I think this leaf is going to start rotating. After all, it's being pushed clockwise on both sides. That's the rotation, right? It's not in the field lines. Circulation is not about field lines, right? Circulation is about, in some sense, all of the fluid together, which I find easier to visualize by what would something do, how would something rotate if dropped into that situation. Okay, I'm sorry. Yeah, you had a question.
Yeah, it was basically like, why are they in opposite directions? But...
Oh, well, that's just, you just got to think through the details of the formula for this vector field, and notice that y is telling you to what extent this points in the x direction. So when y is positive, which it is over here, y is positive over there, so it's pointing a positive amount in the in the x direction. Whereas on the other hand, over here, y is negative. That's right. And so it's going in the negative x direction, which is into the page.
So technically it's circulating like this.
Do what now?
It's
yes. The circulation is what you might call clockwise as seen from above. I'll point out that circulation, let's see here, the circulation is kind of like this. And if you look at the curl, which is downward, right-hand rule. Yes?
Does the actual number that you get when you do the cross product mean anything?
Like the magnitude? Yeah, that's right. So what I can't do in this course is get into specifics of units and, how would we quantify exactly what we mean by the magnitude, because every situation is different, and there's a million such situations, and it's I'm going to call that somebody else's problem, right? So when you get into an engineering context, whoever decides to use curl for a specific engineering purpose will quantify that tailored to that circumstance. All we're going to say in this course is that the greater the magnitude, the more, in whatever sense, the more rotation there is. Yeah.
What if there are more than one curls in the vector field, like two axes?
I don't understand. So the curl is a formula, and the answer is always going to be a vector.
So it's just like
it's
one
a
single
formula.
vector. So there's only one spot in the whole field where when you drop.
No. It depends on where you are. I mean, so at this point, the curl is this, right? But if you were to compute the curl somewhere else, you might get a different formula. Now, in this case, it doesn't. In this case, you can clearly see the curl's constant, right? But in general, if this is a different formula, then the curl might have position the curl might be a function of position, and then you'd get a different vector for different places. Yeah, that's right. All right. Okay, moving along. Again, all of that's kind of premature. We'll make a lot more sense out of this stuff in Chapter 7. Why are we doing this? Right? Why are we sitting around talking about things we're not really prepared to discuss? I think it's actually a really good question. I think there's a pretty good argument on both sides as to whether we should or should not even do this section at all. But I think it is healthy, again, to let those ideas start sort of stewing in your mind. Here's another idea that I want to have stewing in your mind. The big point of what I'm about to show you here is just to raise an eyebrow, to get you curious, to try to persuade you that we are currently sailing over very deep water. There are some very significant, very heavy ideas lurking underneath, right, that we have not yet seen, right? And I'm going to just try to point out just a little bit of that, a lot of which actually we will discuss in Chapters 6 and 7. Okay, so we can compose these three operators. So gradient, curl, and divergence. And just observe, gradient takes a function and gives you a vector field. Curl takes such a vector field and gives you another vector field. And then divergence takes a vector field and gives you a function. That's just what that's what those operators do. So the Legos fit together. So this composition that I've got here is something you can do if you want to. And so, for example, you could talk about taking a function, computing its gradient to get a vector field, and then subsequently computing the curl of that gradient of that original function. And here's one of the weird things that happens. You'll always get 0. Now again, that's just an eyebrow raiser, right? I don't have a punchline here, right? I'm not going anywhere with this particularly, other than again, I just want to make sure that we're all aware that there's lurking points of interest underneath all of this, right? So I think that's an eyebrow raiser. That's weird. That always happens. The curl of a gradient is always 0. And there's more than that. Here's another example. If you have a vector field and you compute the divergence, and if you get 0, I claim. Now, yeah, you see the asterisk here. There's regularity issues and a little annoying little counterexamples. I don't want to worry about that right this second. All of that aside, you take the divergence of a vector field and you get 0, that means there must be some other vector field whose curl is the original vector field. That's another sort of weirdly true fact. So the nice summary of this, to me, I think this is a little metaphor that either I came up with or have remembered from so long ago, I don't even remember where or if I'm remembering it. But everything has a lifetime of 2. And what I mean by a lifetime is if you have something here and then you compute, we think of each operator as suggesting, in my little metaphor, the passage of 1 unit of time. It's just a metaphor. Don't overthink it. Right? And if you get something else, and then if you apply the next operator, you get 0. I'm going to call this a lifetime. This is what I'll call birth, survival, and death. It's just a metaphor, right? A little dark, but anyway, 0 to me is nothingness from which you cannot return. It's kind of like death, right? So anyway, everything has a lifetime of 2. And that encapsulates several facts that we've already talked about. So, for example, you take the gradient, you get something else, and then you take the curl, you get 0. The lifetime was 2. Also, if you have some vector field whose curl, now let's just say hypothetically, let's suppose the curl is 0. That's the death That means this must have been survival. That means the birth must have been back here. That means there must be some function whose gradient is my original vector field. Because everything has a lifetime of 2. It's a weirdly consistent property. Now, counterexamples, yes, just for the sake of completeness, take the exception of constant functions. It's a little bit annoying, but if you think about it, if you have a constant, you take the gradient, you get 0. That's the sad little story of a lifetime of only 1. But that's, other than regularity issues like differentiability problems and stuff like that, this is the only counterexample. So, kind of interesting. Okay, so again, deep water, and we will fill in a lot of these, a tremendous amount of reasons why this is true that I have not even begun to scratch the surface of. All that will come in chapters 6 and 7. Did you have a quick something?
Oh, yeah. Like, why do you call curl a vector field? Isn't it just a vector?
Nope. Curl of a, the curl, right? When you compute this curl, notice what you're going to get is a bunch of terms, every term of which is going to have either an E1, E2, or E3 in it, and those are vectors. Yeah. Okay. So the curl of a vector field is a vector field.
So those examples we have, you're just substituting numbers in, which is why it's a vector.
And I don't know what you mean by that. I am computing the curl explicitly here, and this is what you get, and it's a vector field.
It's a vector field?
Yeah.
But like, isn't it just...
Let's talk after class.
Okay.
Yeah, this is a detail that we can pound out after class. Okay. So that's again, my goal in all of this is just to persuade you that there's a lot going on here, and I think it's a sufficiently mysteriously sort of oddly consistent pattern to suggest there must be stuff going on that we haven't seen yet, and there is. So please be open-minded. When we get to chapters 6 and 7, there's going to be a lot of connections and facts there. Okay. All right. So on to chapter 5. Wait a minute. What happened to chapter 4? Back to the content syllabus. We finished chapter 2 not long ago. Now we're just finished chapter 3, except for 3.1, which of course we did a while back, because I like to use 3.1 in the chain rule. Right? And no chapter 4. So I want to let you all know we are going to do chapter 4. It's just that we're going to do it at the very end of the course. We're going to do it after chapter 7. What an odd choice, you might be thinking. The reason for this is because chapters 6 and 7 is the part of the course that takes the most time to digest, and unfortunately, it's also the part of the course that uses the most prerequisite material. Right? So, chapters 6 and 7 are going to include a bunch of stuff that really makes significant use of stuff we're going to do in chapter 5, which made significant use of stuff we did in earlier chapters and on down the line. So it's hard to do chapters 6 and 7 early in the course, but it's best to do it as early as possible so that you can have as much time as possible to digest those ideas. So chapter 4, as it turns out, is not prerequisite really at all to any of the rest of the stuff in the course, so it's easy to delay it until the very end, and that will give us a little extra time to digest chapters 6 and 7. Okay, so that's what's going on there. And then back to, where am I? Yeah, chapter 5. Okay. So, integrals. Let me remind you how we covered derivatives in this class, right? The very first thing we did when we were talking about derivatives is partial derivatives, which we eventually had to recognize, okay, it's computationally convenient, but ultimately it's very limited in its interpretation, and there are much more powerful and ultimately more natural ways to think about derivatives. Ultimately, there's just no getting around the fact that derivatives are derivative matrices. That's the most fundamental way that you can relate input changes to output changes, namely input vectors to output vectors. That's what matrices do. right? But it took us a while to kind of build up to that. So same kind of thing is going to happen here. I'm going to start off with a tool that will be computationally useful, something we will need. This is not a waste of time, just like partial derivatives, right? But what is ultimately not the best primary point of view on what we're really going to be doing, right? So again, full disclaimer, it's don't hang your hat on what you're about to see here. This is something we're going to need to kind of compute stuff, but there are importantly essential bigger ideas that are way better that we're going to be coming up with a little bit later on, as in probably Wednesday. Okay. Alrighty. So y'all remember this right here, I'm sure, if you have an area and you then rotate that area to generate a volume. And if you want to compute that total rotated volume, right? Everybody remember these? What do they call these? Volumes of revolution or something like that? Yeah. Well, the big idea is you take that volume and you cut it up into chunks. And the entire, whatever that is, volume, I don't even know how to describe that. It's like I don't know, it's a weird shape, right? But these slices are actually really easy to describe, right? I mean, they kind of look like coins. They all look pretty much the same, and computing the volume of one of these is really no big deal. It's area times thickness, right? Everybody happy? Okay, well, let's try to apply that idea to a different situation. And what I want to describe here is, let's suppose that we have a surface, specifically a graph. And suppose I want to compute the amount of volume under that graph, and specifically the volume under that graph sitting over a particular rectangle. Right? How would I compute that volume? And it's a weird shaped volume, and so it's a reasonable thing to try would be like, how about we just kind of slice it and then add up the volumes of the slices? Seems like a reasonable thing to give it a shot. And here we go. You take a slice, you look at a little slice of volume like this, and we kind of run into a dead end. Because, well, I can say area times thickness, but I mean, how do I compute the area? I mean, back here we relied on the fact that this area is a barnyard variety, garden variety, geometric shape. It's a disk. The area of a disk is an old known formula, nothing to it. Whereas this is not. It's not a rectangle. It's not a disk. It's not a triangle. It's not a square. It's what do we do with that? Right? Okay. So here's the idea. If we're just a little bit, persistent on this, I claim we actually can compute this area without too much trouble. That area, if you think it through, it's the area under this curve. That curve came from some surface. That surface was a graph. What do I really need in order to be able to compute this area? I need to be able to talk about the height anywhere I might experience as I move along sort of the shadow, if you will, of this curve. And that height is the height up to this curve, which is on the surface, which has this equation, and z is f of xy. So I have a formula for the height. That height is the function whose graph I was looking at in the first place. So this is actually pretty straightforward. All I have to do is kind of move along that shadow there that I'm highlighting in purple. In other words, let x range from A to B. And as x goes from a to b, and I've got to make sure to keep y at, whatever value that is, wherever it is that I want to compute this cross-sectional area, yeah, sure, y's got to stay that. And if y stays fixed at that value and x goes from a to b, that moves me right along this little line segment. I've got a formula for height, and then area, let's see here, I guess I'll use orange. The area of that cross-section is just that integral right there. What do you think? Let me bring up a complaint, right? Something you might be worried about. I was worried about this when I first saw this. And that was, wait a minute, whoa, hey, that, I've seen a lot of single variable integrals, but I've never seen one that had two variables in the integrand, right? That seems kind of like a little concerning, right? Let me try to persuade you that's not what's happening here. There are not two variables in that integrand, right? That's just the cosmetics. Because you got to remember, y is fixed, right? And it says so right here, y is fixed. Why do I know y is fixed? Because I have to fix it. I have to settle on a single value of y, at least one at a time, right? I've got to momentarily fix a value of y so I can even talk about that cross-section in the first place, right? So y gets fixed before we even try to start computing that area. So it's an illusion to say that there are two variables. Y is fixed. That means that y is a constant. That means that this is an integral of one variable. The variable is x. Yeah, there's a constant in there. There might be several constants in there. There could be some k's and some c's and whatever. But the fact there's a y, that's just a letter later in the alphabet, but it's a constant. Is everybody buying that? Okay. Yeah.
Wouldn't y have to change?
I'm sorry, what now?
Like, wouldn't y have to change?
Yeah, well, that's right.
Yeah.
Eventually, it will have to change. So we'll get to that. But for a given value of y, right? And I have to pick a value. If you were to ask me what's the cross-sectional area, I would say which cross-sectional area, and you would say, okay, y equals 2.6, and then I would say, you want to know the cross-sectional area where y is 2.6. Okay, now y is fixed. And then I compute that cross-sectional area. Yeah. But yes, you're quite right. It will be a variable as I look at all the slices and add them up.
Yeah. So we're gonna have to sum up all the slices of the
Yeah, that's right. That's right. And we're gonna do mechanics in just a minute. Yeah. Okay. So yeah, it's kind of all over, but the shouting and the sort of reevaluating. We've got this cross-sectional area, and just like we saw in this example here, where the integrand was the cross-sectional area, right? Well, likewise, here, the integrand as y ranges over all the numbers between c and d, right? As y goes from c to d, my integrand is this cross-sectional area for which I have a formula there. And what's weird about this is that means that I've got an integral whose integrand is itself another integral. And again, that's another creepy first-time experience, perhaps, for many of y'all to have an integral inside of another integral. So a little bit weird, but that's what we've got. Yes?
Does it matter if you fix x or y first?
That's a great question. It's going to turn, ultimately everything matters, and we're going to see some examples probably on, let's see, today's Monday. So Wednesday, we'll see some examples where, it really does matter. There are some situations in which it doesn't matter, and we'll talk about that a little bit later on, hopefully later today. Yeah. So, not quite a simple answer, but yeah, we'll totally address that. Okay, now before we get into details and computation, let me point some things out. When you're talking about the inside integral, that integral right there, keep in mind the purpose of that inside integral is to represent, for this example that we're doing here anyway, a cross-sectional area. That cross-sectional area makes sense only if you fix which cross-section you're looking at. And which cross-section you're looking at here is y, and that, in this case, again, as we're doing it, is the outside variable. And this pattern holds no matter which way you slice, no matter what happens later on as we generalize this idea. When you're looking at the inside integral, the outside variable is a constant. You treat it as a constant because you'd better, because it is. Right? Does that make sense to everybody? Again, has to be. Right there in the picture. Okay, and then I've already kind of used this language here. Let me talk about this a little bit. Try not to say first integral, second integral, because notice when we were developing this, we wrote down the outside integral first, and then the inside integral second. But when it comes to actually cranking this out, can I start by evaluating the dy integral? Nope, can't. I don't even know what its integrand is yet. I kind of have to do the inside integral first to see what that is then as a function of y, which will be the outside integral's integrand. So you develop the integral outside in, you compute the integral inside out. So first and second doesn't make any sense. It's ambiguous. So you really got to avoid that language talking about the first integral or the second integral. I don't know what that means. But if you say inside or outside, that removes all doubt. Okay. Okay, let's do an example. We want to compute here volume under the graph. Right? Graph of this particular function there. I should circle all of that in green. There's my surface under which I want to compute the graph. Let's see, sitting over a rectangle. I'll come back and talk about that notation in just a second. So we recognize the situation here. We've got a graph. We're going to compute the volume sitting over a rectangle. And we already know the answer. We already did this argument here. You want to compute that volume? Cool. That volume is iterated integral. So we just write this down. We don't have to go through the process again. We've already showed that this does it. Okay, let's talk about that notation. It's a little bit of a weird notation. I claim that this notation represents this rectangle right here. I have to grant that symbol, the kind of the times symbol, we've used that previously in multiple ways, and ultimately there's just more mathematical concepts that need a notation than there are reasonable letters in the alphabet and symbols in the typewriter. There's only so much we can do. So certain symbols get used over and over again. This is one of them. In this context, what that means is the first interval is representing the range of values of the first variable, that first variable being x in this case. And then the second interval here is indicating the range of values of the second variable, in this case y. So the interpretation you make here is we're looking at all the points in the xy plane where x goes from 0 to 1 and y goes from 1 to 2, and this is that rectangle. Everybody see what we're doing here? Okay. So this is a pretty common notation. We're going to use it a lot in this course, so heads up, you got to make sure you know how to interpret that. The computation is pretty straightforward. We're going to start by computing inside out, starting with the inside integral. It starts off pretty straightforward. When you're integrating, right, how do you integrate x squared? Well, the integral of x squared is 1/3 x cubed, yawn, boring. Everybody knows that. And then with perhaps too much confidence, we go along to y squared, and it's tempting to think you're going to get 1/3 y cubed, and you don't. And that's a landmine, right? That's a risky little moment. A lot of people mess this up. What do you do here and why? Well, keep in mind, as we discussed here, for the purposes of the inside integral, right, the outside variable, that outside variable is constant. We treat it as a constant because it is literally a constant. So this y right here, and therefore this y squared, constant. And the integral of a constant, antiderivative of a constant, is constant times, constant times the variable. Variable being x because it's a dx integral. Everybody on board? Easy to mess that up. So you got to be really careful about this. And by the way, that's your job, right? You got to just take responsibility for. Y'all are going to be computing bazillions of these kinds of integrals, not only in this course, but throughout the rest of your, life in technical fields. And you just always have to keep your eyes open for this little issue. So anyway, there's that. Okay. All right, fine. So this is the integral, the antiderivative. And then let's see here. Now, again, the next thing y'all are accustomed to doing when you have a single variable integral is you take the bounds and you just recopy the bounds, kind of like that. And then the idea is you're going to take this number and plug it in. And then you're going to take the other number and you're going to plug it in, and I've already screwed up. What did I do wrong here, right? I mean, isn't that the deal, right? You take the numbers, the 0 and the 1, and you put them there, and you plug them in, and okay, yes, but don't forget what's a constant and what's actually the variable in question, right? So this is all wrong, erasing all of that. Y is the outside variable. That means y is a constant. That means that y right there, constant. You don't plug in for it. Treat it like a 6. You don't plug in 1 for 6. Right? It's just a constant. So what you do, of course, is yes, you do take that 1 and you plug it in to there and there because those are the values of x, because x is my variable for the purposes of this inside integral, right? So in order to help myself keep track of this kind of thing, and don't get me wrong, I mean, I understand mathematically, fine, right? But I am susceptible to oopses, as are we all, right? And so I encourage y'all, just in case, just to try to keep this to a minimum, don't just write 0 and 1 like that. Go ahead and write specifically x equals 0 and x equals 1, and then, again, having been careful enough to write that down, you will not be tempted, probably less tempted anyway, to plug in where it says x equals 1. It wouldn't feel natural to plug that in for y. Yep.
We also just bring y, bring it out of.
Well, it's like any other constant. So in this case, for this integrand that we're looking at, it's not a multiplicative factor. It's just a multiplicative factor in one term. So yeah, it doesn't. It's only multiplicative factors that do that. Now I could separate this into 2 separate integrals, and then yes. But for the moment, I think it's best to just leave it where it is. Yeah. Right. Yeah. Okay. Okay, so those are the 2 landmines. Everything else is pretty straightforward. Let's see. So, you evaluate all of this, and it ends up being this expression right here. That is our inside integral. We move along now to computing the outside integral, for which our variable is now y, right? Y is literally going from 1 to 2. Y, now that we've done the inside integral, y is no longer a constant. Now y is the variable. Does that make sense, everybody? And so now, I know this seems so weird because, we made a big deal about how the integral of y squared was not 1/3 y cubed, but now we find ourselves again needing to look for the integral of y squared, and now it is 1/3 y cubed. Because y is the variable now, as opposed to previously it was a constant. Okay, and you plug in your numbers and fractions and all that. Y'all can check those details. Okay, everybody happy with this computation? Okay, so somebody asked earlier about can you do this in either order, and in some cases you can. All we've entertained right now is the idea of rectangular domains, and so yes, in fact, this that we just justified, computing the volume with an iterated integral with the dx on the inside and the dy on the outside, that happened because we did our y slicing. We started our slicing process by slicing perpendicular to the y-axis, constant values of y, what you call y slicing. But yeah, you can slice it the other way, and you get you get a bunch of different details. But yes, you can go through and compute doing your x slicing first, right? dx on the outside. You get a geometrically different picture. It's highly analogous, but different, right? And it's a wonderful exercise to go think through, draw what that picture would look like, think about the differences and which variable is a constant at which part of your argument, and what you end up with is that right there. Yes?
Yeah, I often calc too, there's some questions whether you can't really choose whether you do x slicing or y slicing. Is that the same for 219, or would you generally be flexible with us choosing either?
You were making a reference to Calc 2?
Yeah, because sometimes the questions would be like, oh, you have to use y slicing to evaluate it. Would that be...
So this must not have been Calc 2 at Duke, because it sounds like you're talking about double integrals?
I know, like, for example, like, calculating the area under the curve, let's say either with the y-axis or the x-axis, like it'll specify.
No, I understand. Okay. So yeah, that's a different situation where you could take a curve and view it as a graph of a single variable function in either of two different ways. I understand now. Right. So yes, it is perfectly fine to do that in either order, and likewise here, it is perfectly fine to do it in either order. Yeah, absolutely. In fact, you should be able to do it in either order, right? And there are some situations where one is much better than the other. Yeah, absolutely. Yeah. Okay. All right. So what I want to warn y'all about here, the dangerous little thing, is it's tempting to say that these two integrals are always the same, and they are always the same as written. Again, we have to worry about regularity issues and continuity and stuff like that. But we are very soon going to switch to talking about non-rectangular domains. Notice everything that we're doing here is assuming that we're computing over a rectangle. And very soon when we switch to non-rectangular domains, this doesn't work anymore. And everything changes in some subtle but important ways. So it is nice to notice that the dy integral and the dx integral, you can just do this. You see what I'm doing with my fingers here, right? So you can switch the differentials, right? But you have to switch the bounds accordingly, of course, because x goes from a to b. I mean, yeah, it continues to be that x goes from a to b. No matter, you can change the order you slice it, but the domain is what it is. So it remains that x still goes from a to b. So don't forget to switch the bounds also. And this, again, only works for rectangles. We are very soon going to see some examples of non-rectangular domains where, in general, this just is not true. it's more complicated than that. Yeah.
So if this rectangle goes across an axis, so there's a negative area and a positive area, do you need to compute each part respectively?
So this is about compute. Yeah. So no, you bring up a good question. So let me go back to here real quick. So I did start off saying, look, I want to restrict our attention to continuous because I don't want to deal with regularity nonsense, and non-negative because I don't want to deal with exactly what you just asked. So yeah, ultimately, if the question is to compute volume, and if the surface like dips under the xy plane, then okay, if our goal is to compute the volume, then yeah, you'd have to break it up into two separate pieces. Ultimately, though, most of the time, it's not what you're interested in. Most of the time, when you have an integrand that's negative sometimes, most of the time you still just want the integral. And this business about computing literally the volume and literally the area from like a Calc 2 class, kind of an unnatural question, really, as it turns out. So we'll see some more examples of that later on. Yeah. Okay. Let's see here. Yeah. Here's a nasty little business. This is bad news. I'm sorry to have to be the bearer. In single variable calculus, we wrote down single variable integrals to compute area under a curve. And then we asked a bunch of other questions like, hey, what if I have mass distributed across an interval? Like, they talk about the mass of a rod example, right? Non-constant density. Or maybe I want to compute the amount of work that it takes to perform a certain task, or the population of bacteria, blah, blah, blah. Bazillions of other examples, and it turned out that the integral we had just developed was exactly the tool that we needed to answer, I'm going to say, all of those other questions. You would be tempted to say, well, now I have a formula for computing volume under a graph of a function of two variables. And hey, you know what? Wouldn't it seem reasonable to speculate that, again, we can compute a whole bunch of other things by the exact same construction? Wouldn't that seem tempting? It certainly would be analogous. And this just isn't true. It's very importantly not true. So let me just, as a for example, in order to make sense out of, one of the very first things that we did in trying to make sense out of this integrand, for example, was we argued that, look, this is height times length. Right? And if I want to know the area, looking at the cross section and just one of those areas of one of those little strips, well, height times length. And that gives me area. And good news, I'm already familiar with the idea of area. Furthermore, I know that area is an accumulating quantity. The whole is the sum of the parts, and you can see it right, whoops, too far. You can see it right here in this picture. If you want to know how much area there is in that whole, you can break it up into little strips, compute the areas of all these individual strips, and the total area is the sum of those pieces of area. So the whole is the sum of the parts. I can see it right there in the picture. That's very convenient because I already understood area. Area was a known thing. Okay, now let's try to make sense analogously. Let's see here. Analogously with, suppose we're computing mass. By the way, just to get the premise set up, suppose we have mass distributed across an area, density being mass per unit area instead of mass per unit length. So in this question, mass is distributed across area, density is per unit area. Okay, so then what does that mean? And, well, the density, mass per unit area, that's the nature of the question. I got to multiply that by a length, dx. But what do we got here? Mass per unit area times length, that's not a thing. And you can probably think through and persuade yourself, maybe you could choose to view this as mass per unit width, something like that. Right? Here's the problem. Bet you never thought of that before. Are you sure you really understand how that behaves? Is that an accumulating quantity? Can I just claim, without any justification being necessary, that I can add that up and that makes sense? I don't think so. So the point is, this argument crashes and burns. We got lucky previously. That area just happened to be a convenient intermediary concept that we were already familiar with. That was a super lucky break. No such luck in this situation, and so we're going to have to find another way around this if we want to do anything other than answer geometry problems. And y'all are engineers, so y'all are going to be computing a lot of stuff that's mass and work and all sorts of other things. So more on this next time. See y'all later. And don't forget about attendance as usual.